So what we're going to talk about for, I guess, the rest of the class is radiation concepts. We're going to go into this third mode of heat transfer. So far we've done conduction, we've done convection. Now we're going to start talking about radiation. With conduction and convection, it's a really easy transition. Because, okay, convection, as you've learned, is really just conduction with stuff moving. Well, radiation is very different, right? Radiation is not like either of those things. It is not, it's something that's happening at a distance. It's separated even by a vacuum, right? You can still have radiation occurring. So the mechanisms that are involved in radiation are different. It means that the way that we model it's a little bit different. So let's now move on to radiation. We're not really going to be talking about heat exchangers or conduction really anymore in the class. Moving on to radiation. So if we remember kind of where we start with radiation, what I've told you this whole semester is pretty much the rate equation is like this. It's Q dot radiation is equal to sigma epsilon AS Ts to the fourth minus T infinity to the fourth. Where this sigma is the Stefan-Boltzmann constant. Epsilon is emissivity of the surface. AS is the surface area, like the exposed surface that's emitting. And then this is the surface temperature. And then this is the surroundings temperature. All right, so this is our rate equation for radiation. And okay, we went through and wrote it in different ways. One way we can kind of rewrite this is Q dot radiation is equal to, again, sigma epsilon AS. We can factor things out where we say Ts squared plus T infinity squared, Ts plus T infinity times Ts minus T infinity. Okay, so when we did that, we could say, well, we can write this as this bit here. This is approximately 4 T bar cubed. That was our approximation, which lets us write it as like a conventional rate equation. The other thing we've sometimes done is said, well, this whole thing here, we can sometimes call this like H bar radiation. It's kind of like a convection coefficient, right? H bar radiation times surface area. But this is really as far as we've gone with it. And I don't really tell you like where did the equation come from? Why is it T to the fourth? What is the relationship? Where did the sigma come from? Right? All this stuff has sort of just been given to you, and you go with it. What we want to do now is maybe understand a little bit in more detail under which situations this is valid, like and how you'd come up with this equation and how you'd maybe change it if something changes in your problem. All right, so I've got a red potato here. My red potato is emitting. So what we want to do is think about the energy balance and where this equation came from. So this thing is emitting, and let's say that this is something called QS out, right? And this is actually represented as sigma epsilon AS TS to the fourth. So when we're talking about radiation exchange, the reason why we say radiation exchange is because I've drawn something leaving, but actually something is coming back to this volume as well, right? So we're thinking about this surface or this volume, so I better maybe draw a control volume just so I'm clear. I have something leaving, it is QS out, but something is also returning. There's radiation exchange happening between this hot thing and its surroundings. So the surroundings are sort of emitting something back. Maybe it's a longer wavelength, right? And this would be Q dot S, let's call the Q dot S in. And that would be equal to sigma epsilon AS T infinity to the fourth. All right, so the net exchange is just what's leaving minus what's returning. So that net would be something like this. It's just our rate equation. So it's Q dot S is equal to sigma epsilon AS TS to the fourth minus T infinity to the fourth. So, okay, this is kind of talking in a circle, right? I'm telling you that there's radiation exchange occurring. What I want to communicate with this is that radiation exchange is the hot thing emitting, but also the hot thing absorbing from a colder thing, right? So it's not the case that radiation only goes one way. It's always bouncing around. It's just that there's more radiation occurring from the hot thing to begin with. So in net, you end up like losing more as it goes out.